Good morning, everyone. Welcome to the Engineering Association's Spaghetti Bridge Breaking Day. Welcome. And we have our equipment all set up, ready to test your bridges. This is a device that we'll put our bridges on. You'll be able to see a readout of the load that each bridge breaks at, and it holds it. And this will be recorded, and we'll be able to get that information to you. You guys one job. Every time I test a bridge, I have to cancel the numbers from before. So if you don't see 00 there, please shout out, let someone know so that we make sure this is on 0 before we start the next bridge. And today I have...
Hello, good morning everyone. I'm Vaishali. Now I'm going to introduce the name of the school. This is the West Park School. And the student name is Joysa.
Okay, and we are both professional engineers, and I'm a civil engineer, designing structural things, worked for Manitoba Hydro for many years.
And I'm an electrical engineer, but right now I'm engineer in intern.
Which means she's going through the last stages before becoming a professional engineer. All right, so welcome. Okay, here we go. The first bridge. And I guess if there's any questions, there is a place online to put them. So by all means, if you have any questions, please provide a comment, and we'll answer your questions as soon as we can. Okay, here we go. And I'm just going to reset it a bit here. Make sure we get the bridge set on the machine right. And here we go. Oh, wow. There we go. All right, 3.3 kilograms. Great. Okay. And next bridge is just getting ready.
Yes, the next person is Matthew.
All right. Very nice looking bridge here. And we got to reset this again. And we'll be able to adjust it. This is a great looking bridge. Perfect. We'll see how much it can carry. Ooh, all right, look at that. Oh, wow. All right, 14.4, great job there, guys. Keep going to the next now.
The next student is Noah.
Okay, all right. And we're just going to adjust the machine here a bit and see what we can do. Anybody got some guesses how much this might carry? Maybe we'll break a few more bridges and you'll be able to get a better feel of what bridges look like and how much they carry. So, all right, we've got 0.5 kilograms there. All right, good job. So you can,
yeah. Okay, the next student name is Jan. Yeah, you can reach.
Right, okay. So I'm not too sure how to test it. I'm going to do it like this, and hopefully that is the correct way for the bridge to be recorded. Yes, can people see it? There we go. And I've got to cancel it again. Okay, here we go. Uh-oh. Uh-oh. Let's see. Well, look at that. It carried 1.1 kilograms. All right. Good. Okay, you can do the next.
The next one is Quincy. Here it is.
Okay, we got to cancel that.
Can you say that name again? Quincy.
Quincy. All right. Okay. Got to gently put it in place here, and we'll see what we can do. Uh-oh. that's about it. All right. Okay. Very good, Quincy.
The next student name is Kaiden.
Okay. And I'm assuming we're going to. There's that, and I believe the bridge is to be tested like this. Hopefully that's the case. I would recommend that as a structural engineer, the best option. So we'll see what it can hold. And yeah, I think that's about the best we can do. I don't think it can hold any more. So officially, I guess it's 0.1 kilograms, but this is going to be unofficial. I'm going to see if I can load it to see what this other portion can actually hold. Now, please appreciate this is unofficial, so this will, if it can carry any more load, this is not going to be part of the competition. But we'll see if the bridge was made a little longer and sat on supports as we initially saw it. It probably would have been able to carry a little more, and this might demonstrate that. So it carried a little bit more. All right, pretty good.
The next student name is Jida. Here is the bridge.
Okay, here we go. And I'm sorry, don't know how the bridge is supposed to work. You know, it could be like this or it could be like this. It's a tough job. I think it may have been considered like this, where you can drive over it. So if it's not quite the way they intended, I'm sorry, but I think I'm going to try it to load it this way and see what we can do. And I think that's about it. All right, 0.7, actually pretty good. Very good. Okay, next one up.
Okay, next one is Daniel. Unfortunately, his bridge is disqualified.
It looks like it's a little too high. And that's something very important to watch for. We do have, excuse me a second. As an example for everyone to follow and or perhaps the next year to make your bridge, this document shows the maximum height and the width based on the grade area. And if we take this bridge and we set it near the bottom, take note that it goes outside the gray area. So that is why this is disqualified. We're still going to break it, but as far as a reward for prizes and so forth, the height of a bridge may have an impact and make the bridge be able to carry more load. So that's why we set this criteria, so that this bridge might have more of an advantage to carry more. But the intent is for everyone to follow the same rules. So that's important, something for teachers, something for students in the future to consider, that these rules need to be followed. And that's kind of just like the same thing engineers have. They have a certain criteria that they have to build things to. If, let's say, if you didn't build a bridge high enough and cars could not drive under it, that would be a problem. So we have to be very cautious in making sure we understand the rules and follow them and make criteria to make things, in this case, consistent as far as how much load they can carry. So sorry about that, but something to learn and pick up for next year. Okay, so here we go. All right, 15.4. Very good, excellent. And yes, any questions on this criteria or understanding why some bridges are qualified and not disqualified, please put a comment in and we can provide some live feedback on that. Thank you. Okay.
Okay, the next person is Ontario. Here is the bridge.
All right, okay. So I think what we're going to do is we're going to test it like that. hopefully that was the understanding. And we'll just raise the mechanism up. And here we go. Oh, there we go. And it looks like we might be able to carry some. So officially it's 2.7, and I don't know if we can get any more out of it or not. Probably not. Well, there's a little bit more there. So if the bridge would have, let's say, oops, we're getting the camera here. If this component at this end here was made a little thicker, a little stronger, like the middle, and extended over top of each end, probably the bridge would have carried a little bit more. So something to consider for the future.
The next student name is Earl, and here is the bridge.
All right, okay. So this looks like a pretty nice bridge. So we'll see how this works. Excuse me while I get it set up here. All right. Okay. All right. 20.6. Awesome. Very good. Great to see. Good job. Good design.
The next student name is Dinah. And here is the bridge.
Right. Okay. Got it set just right. Oh, I don't think we can get any more out of it. Yeah, I think that's it. 3.5. All right. Great job. Excellent. Excellent design. I see lots of triangles. That's a good clue for a good, strong structure.
The next student name is Ty. Here's the bridge.
All right. Okay. I'm just going to turn this around like this. I'm going to set this up. And I'm going to load it on this one point here. I could suggest that you see how we have sort of two triangles going, but they don't touch exactly the same spot. If it was reconfigured so this point and this point coincided onto the exact same point, it might have made a little bit of difference. Something to consider for future designs, but we're going to see what we can do here. I think that's about it. Yeah, we're crushing the top, and that's about it. So 10.8. Very good. Excellent.
The next student name is Saina, and here is the bridge.
All right. Okay. Again, we're seeing this very classic triangle shape. So awesome to see. I suspect people are realizing, students are realizing that this is a pretty good solution for building a bridge. So, whoops. We'll see what. Oops, man. We'll see what we can do here. Good design, right height, right span. Notice how it sits over top of each support a little bit. So that's a good design. All right. Very classical break. Look at that. 14.1. All right. Great design.
Okay. The next student name is Matt. Here is the bridge.
All right. Okay. Any comments coming through? Any questions anyone has? Oops. Just get it adjusted a bit there. Okay, here we go. Any guesses how much this is going to carry? Uh-oh. I see something breaking already here. I think that's about it. 1.4, pretty good, pretty good. Nice design.
The next student is Dishan. And here's the bridge.
All right, okay. Okay, something like this. I see lots of glue here and there. That's really important to have the right amount of glue. The idea is the glue is working to hold the spaghetti together. They work together as a team, and getting the right amount of each one can optimize the design of your bridge. I'm going to see if I can reset this. Maybe it's long enough that it can still span a little bit, and we'll see if it makes a bit of a difference. We're at 2.9, so this might be the official load. I'll see if there's any change here now. Okay, there. It officially broke. So I guess the official load there is 6.8 kilograms. So great job.
The next student name is Aiden.
Okay, thank you. So just a comment here. Take note that it is a triangle shaped, just like many others. But take note the way the instructions show that we're going to be loading it in the center. The problem is the top of the A, which would be the strongest point to add a load, is off center. And if I was to move that to where the load is, take note that one end wouldn't be sitting on a support. So it's a little bit compromised because we're going to be loading it on a point here and not necessarily where the triangle tip comes up. So next time a bridge is built, take note. But we'll see how much this one can carry, as is. Oh my goodness, 2.0. Okay, great design. Just tweaking the configuration a little bit could probably make quite a difference. So for the next time.
Okay. Next student name is Isha. Yes, bridge.
Okay. Now again, take note that with this again, we see the bridge is long enough, but take note that some of the major structural components are a little bit short, even though there's a couple pieces that are long enough. If the bridge was built that would sit like this, and sit like this, it would probably carry a lot more. So, but we're going to have to set it up like this and only be supported on these few pieces and not on the major pieces like we have here. So I don't know if we're going to be able to get any load because those couple of little pieces on the end really don't, they're not going to hold too much. And again, the triangle is kind of off center. I'm just going to kind of manually push it here until the pieces break. And you can see that now the bridge is too short. So officially, I would say 1.9 kilograms, but I'm going to now unofficially try to load it just to give a student an idea of what a bridge design like this could have done if the configuration was just tweaked a little bit more. So here we go. And again, the problem is the triangle doesn't hit quite in the middle. So we're going to have to kind of adjust this a bit. So this kind of proves what the design might have been able to carry if it was just constructed a little bit differently. And there it's quite a difference. So, but that is not the official load for prizes, but at least it gives you an idea of the design concept that the designer had in this case. It was a good design, just implementing the manufacturing of it in just a little bit better way could have made a huge difference.
Okay. The next student name is Dylan. Yes, bridge.
All right. So I can see that the bridge is long enough. They've obviously considered with these extra pieces at each end where it sat on the support. It's a nice triangle shape. I'm going to have to slide it a little bit off here again to get to the peak of the triangle right where the loading is going to occur. So let's see what we can do here to optimize it. I cannot turn this like this because that would be kind of cheating a bit for other bridges. That would give an unfair advantage. We have to keep it in this direction so all bridges are being tested in exactly the same way. So considering that this is going to barely touched the right peak. All right, we'll see what we can do here. Oh, I gotta reset it.
John, the students are rooting for this bridge, apparently.
I'm sorry?
The students at West Park School are rooting for this bridge.
Oh, right, okay. Good. Okay, we'll see what we can do here. It looks like a good design, so maybe that's why everyone is rooting for it. Here we go. All right, you can see it kind of came apart in the center, very classic. So 9.6, very good. I can also see, there's places here where the spaghetti is kind of working by itself, and if there was more glue added, right here, more glue added, it could have made quite a difference to it as well. So make sure you get lots of glue. Oh, excuse me a second. Gonna clear some spaghetti here that's flying around. Go on a trip on a bridge.
Okay, the next student is Slater.
All right.
Yes.
Okay. So this is kind of interesting. I see they got some neat reinforcing in the ends here with a different concept, not big long pieces of spaghetti, but kind of broken up to get it like a matrix. All right. So we'll see how this design works. Take note, this bridge is kind of unique in that you can drive over it. It's designed with a deck, as I would call it. So that makes it more perhaps practical than some of the others, but not necessarily a criteria for the competition itself. We'll keep, okay, so 1.7 I'm going to consider as the official load because the ends have now failed. But we're sitting on this span here that makes it a little shorter. So I'm going to continue breaking it, see what it can ultimately carry. It may not carry any more, but we'll just try it. I think it's all broken already, so that's about the best we can do. And so good design, good concept. Very nice.
The next student name is Alexandria. Looks like she made a nice piece.
Yeah, this is very intricate. It would take a long time to build and to get it all together, but yeah, it's very classic A-frame with lots of integrated pieces and so forth. A shame, it looks so beautiful. Shame we're going to have to break it or crush it. So here we go. Now take note that this bridge is quite a bit lighter than some of the other bridges that we've broken. So you could expect that maybe this bridge wouldn't hold the same amount as compared to a heavy one because its own weight is very light, and that has a kind of a ratio thing kind of going. Obviously the more structural members you have, the heavier the structural members, the more load it's going to carry. So this would be very unique. And maybe the load won't be as high as some of them, but take note, the design is very nice, very intricate. I think that's basically all we're really going to get. I think it's failed, and even if I keep going, it's not going to make that much more difference. You can try, but I think there's limitations on the testing machine. Yeah, it's just going to continue failing. So I guess it's broken. Sorry about breaking it, but 1.7. All right, very good.
Okay, after then, this is the last student, Marcus.
Last student for which school?
West Park.
West Park. Okay.
Yeah.
So I see some loose pieces here, and I'm sorry. I suspect that maybe it might have got damaged in transportation. So sorry about that. We're going to try to break it, and maybe I could see some aspects of triangles being created here on the side of a bridge. Looks like a great design, a great concept. Maybe the manufacturing of it, glue, when you put it on spaghetti, it makes the bridge, or makes everything kind of warp a bit. So I can appreciate it makes it a little more complicated to build, but that's part of the challenge in building a bridge. So we're going to see what we can do here. And loading this and see what happens. Oh, there we go. All right, 4.0. So very good design. I think the design is there. It's has some great start to it. And if everything would have been completed maybe by the original design concept, probably would have done a little bit better. So nice to see being built.
Okay, now we are going to start the new school, Amber Trails Community School.
Welcome, everyone.
Welcome, everyone. And name of the student Anish and Gurnar.
All right. In case you just may have come online, my name is Don Spangolo. I'm a professional engineer. I am here to use this machine to break your bridges today. I don't know if you've been able to catch any of the other bridges that we just broke from another class, but this device will set the bridges on and we will break them and test them, and I'll give you some hints on how to maybe make them a little bit better later on. And this is my helper today.
Hi, I'm Vaishali. I'm an electrical engineer intern here. I am going to be professional engineer soon, maybe.
All right. Yes, there's a bit of a training process after completing at the university. So this bridge is meeting all the criteria. Some of the bridges, I'm just looking at the others. There's certain criteria. The bridges have to be long enough and not too tall. And if we come across a bridge that maybe hasn't met the criteria, I'll explain that. But this one looks good to go and will be ready to potentially win. Oh, all right. I've got helpers here. Good. Thank you. Thank you, everyone. Okay, here we go. Any guesses? It's being crushed. I think that's about all we can do. So a great design, 8.0 kilograms, very good. I could suggest glue, lots more glue. Yes, a lot of the spaghetti kind of just is sitting there by itself. So please make sure that you get lots of glue in the joints and where things fit together, and that will make the bridge much stronger. All right.
Okay, now next students are Arav and Nav. And yes, great.
All right, very classical triangle shaped here, very good. And I'll try to remember to do that again. All right. Here we go. And I think we see, yeah, I don't think we're going to get any more out of it than that. So 3.8 is the official load. So great design. Thank you.
Now next students' names are Davinder and Sahaj.
All right. Okay. All right. I feel some weight here. So hey, this might make a difference. There is a criteria for a maximum load for the bridges. I guess this one meets that criteria, but I guess the more spaghetti, the more glue you have, there's more strength in the bridge itself. So we'll see how this one works. All right. Okay, there we go. 10.0, excellent, very good. Great design.
Okay, now next students are three students, Kailani, Lion, and Skylar.
Okay, guys. Looks like a good bridge. And cancel this. And here we go. Any guesses? Oh, I feel here's some cracking. All right. Wow, it exploded. 9.5. Great. All right. Going to clean up a few things here. Just a second.
Okay, now the student name is Kaina. And yes, bridge.
All right. So everyone enjoying themselves? Is this kind of exciting to see? Please add any comments if you like. Here we go. Guess looks like the best we can do here. All right. Okay. Now 2.0. Now I think it's a pretty good design. Like that's pretty good. Except notice that at the joints between different pieces of spaghetti, how easily it fell apart. Again, I stress glue. A little more glue in those critical spots. And I think your bridge could hold quite a bit more. So for the next one, remember, lots of glue.
Next students' names are Gunit and Inayat.
All right, okay. Okay, here we go. This looks pretty good. We'll see what happens here. All right, whoa. Major explosion, 12.3. Very good, excellent. All right. Now take note that we are using up a lot of spaghetti here. And so what the association is doing, all the bridges, every bit of load that they carry, we're adding this up. And as you can see in the background, 6,241 kilograms is the amount of load that all the bridges we've tested all week has added up to. We're going to be using this kilogram count to make a donation to Manitoba Harvest for them to purchase a food product for all the needy people. Might be in some cases pasta, or spaghetti, but there's many other needs that people have. But we're donating this to kind of offset the spaghetti that we're kind of using here that may have better uses to eat, but we were trying our best to provide something for your students to do. The spaghetti, of course, is very simple, something you have in your own kitchen to work with, and but it's very important for us to support our community as well. So the more your bridges carry, the more we are giving to Manitoba Harvest. So there's another goal for you.
The next students are Dominic and Joshua.
Okay, see what we can do here. Looks like a pretty good design. And, oh my goodness, yes, all right, again, a little more glue and all these pieces that kind of fell apart would be great. And I think the bridge could have held a lot more than 3.2, but great job, great design. Just a second, I'm clearing some spaghetti where my feet go just to make sure I don't trip. All right, okay.
Okay, the next student is Canison.
All right, here we go. Looks like a good design. I see lots of glue in certain places, so we'll see if that helps and how it breaks. All right, 5.9, pretty good, great design. So good bridge, good job.
The next student is Meta. Yes, bridge.
Right. Okay, I see some interesting details. I see a little reinforcement pieces put at each end. A great job, and I see another little plate kind of added here to just kind of make sure that all the pieces are connected together. So a great job. I see some good thought process going through designing this bridge. But the machine always wins, and it breaks the bridge. I'm sorry. So 2.7, actually very good. All right.
Okay, Meta was the last one of the school Amber Trails community. Now we are.
So thank you guys for coming out. And I guess if you want to stay online, that's up to your teacher to watch and see some more bridges breaking. But thank you for coming out.
Okay, now the school name is Victor H.L. White School. Welcome everyone. My name is Vaishali. I am an electrical engineer intern here. And
Hi, I'm Don Spangalo. I'm also a professional engineer, and I'm here with this machine to break your bridges today. There's an electronic device that was going to show the peak load that the bridge carries just before it breaks. And I have a job for everyone to make sure that I zero this out every time we do a bridge to make sure we start at zero. And I see we're using spaghetti here, so I just like to make a comment, a shout out that you can see just behind me, there's 6,254 kilograms. That is an accumulation of all the load that all the bridges that we've tested and broken, over this last year. And what we're doing is, depending on this total weight, we're going to be donating funds to Manitoba Harvest for them to buy food for the needy. It may not necessarily be spaghetti, but they will determine what best use the resources for. All right, thank you for coming. And here we go, the first bridge.
okay, the first bridge of student names Logan and Korshin.
So what I would like to note, this bridge is disqualified for prizes because the criteria for building a bridge required a certain span and a certain maximum height. And I guess some of these bridges may have inadvertently been built a little too high. We can still test it, it still fits into the machine. But as far as winning prizes, what we're trying to do is make all the bridges and the rules consistent. You can appreciate the taller the bridge, that might give it an advantage in being able to carry more load because it has a higher depth to it. So the idea is to make sure we don't go beyond a certain limit to make it consistent and fair for everyone. So we're still going to test it. It's still going to be recorded, but take note that these bridges that have been built beyond the criteria, they will not qualify for prizes. So please take note next year when you build them that you follow the rules, follow the specifications, and exactly what engineers have to do too. They have certain specifications they have to follow when they're building and designing components. And we got a 0. And here we go. Looks like a good bridge. All right, I think 7.3. All right, very good. I'm not going to continue testing it because a major portion of the bridge has already failed. So I think we have to consider that this 7.3 is the actual load that it was able to carry. But thank you. Great design. I see lots of little triangles. That's a good design.
Okay, now the next student is John George. This bridge is also disqualified.
Okay, because of its height. Now, I guess another component I can see here is that it has to have a minimum span. Again, a specification that's noted in the documentation. And the reason for, of course, if the bridge doesn't span this span here, we set it down here. Again, it's to its advantage because it doesn't have to span as far. It doesn't have to be as strong to carry an equivalent amount of weight. So if it's too short or if it's too high, we consider that these are things that make the bridge more efficient and not consistent with the bridges that others are making that do qualify or do follow the specifications. So I'm still going to break this and take note that it's sitting down in these lower portions here. This machine has been specially designed to accommodate the odd bridge that maybe is not built within the specifications, but it's still very important for the student to see what his design can carry. So again, we'll see what it can carry, but this will be an unofficial loan as far as the prizes are concerned. A few pieces are breaking here. Just give me a second. I'll see what I can do. Yeah, no, it's already failed and fell apart. So 0.7 is the load it can carry. Again, make sure students, maybe teachers as well in helping the students put this together is to make sure you understand the design criteria and why that's important to follow those. Thank you.
The next student name is Baldwin.
All right, and here we go. I can see that it spans correctly, and it looks like it has the right height. So this one is qualified for prizes, but of course, oh, sorry, it is a little too high. Excuse me. I guess it's the same as the last one. Same understanding, same criteria. We're going to test it. Nice to see that the length is there. The height again is a little off, which gives a little disadvantage. But we're going to test it anyway. Okay, yeah, I think that's what we could do. So 4.6. Great design. Again, follow the rules just a little more closely, and next time maybe you can learn something to build your bridge a little better by watching all these other bridges that are being broken and get some ideas of what works better than others.
Now, next students are Omar and Shuhin, and this bridge is also disqualified.
Okay, so again, I guess we're dealing with the height concern here. Same thing. So sorry about that. And I'm going to cancel this, and I'm just going to kind of sneak this in here. There's a little bit of glue that I really can't move it to get it to fit into the machine. So I'm just going to give it a little tweak here. There we go. So you might see a little load there come on. Okay, now we'll test it. So great design again. Just the height became a bit of a problem for it. All right, now you can see the ends crushed. So great design. Look at that, 11.1. So good design, just a little high. So sorry about that. Next time you'll know what to do.
The next students are Yasmin and Morapeda. This bridge is also disqualified. Sorry.
Oh dear, oh dear. I guess looks like some of the students are kind of copying one another and ended up with a few bridges being over in height. So we're really sorry about this. But to make it fair for everyone, we've got to make sure that we don't build things beyond specifications. So I'm going to add a little load to it just to get it into the machine, because the machine is obviously designed for bridges that fall within the criteria. And I think that's it. So 5.0. So great design, good concept. I think the construction looks pretty good. But again, watch the height for next time. Thank you.
Now, next students are Sophia and Jediha.
All right.
Good.
And okay, so this bridge, you can see it's shorter and it now falls into the criteria. So all right, so this bridge will be entitled for, depending on what it can carry, for prizes. There you go. Looks like a great design. Lots of good pieces fitting in the right places. I think there's some pretty good glue, and look what happened to the load that it can carry. All right, look at that. Eh? Very good. See how it failed? Excellent job, and how it's all put together. So great, 35.6. Oh my goodness. I think that's about the highest bridge that we've tested so far today. So congratulations, guys. All very good, very good.
Okay, now, next students are Mohammed and Trust. I'm really sorry this is not qualified for.
Okay, again, because of height, yes. Okay. All right, so here we go, and we'll see what we can carry here. There's a little bit of load in there, but it's already preloaded because it's a little too high to fit in the machine. But obviously, we've got a lot more load to come onto it. So look at that. Excellent. Beautiful design. If it was just a little shorter and qualified, all right, this would be very competitive. Great design. You definitely know what you're doing in putting this together and how the pieces are intertwined. Cool job of how you've interlaid it. So definitely you know what you're doing. Great, great to see.
Okay, now, next students are Ahmad and Dean.
Right.
That's the bridge, and this bridge is also disqualified.
Okay, again because of height. Oh my goodness, yes, it looks like everyone is just just that little bit too much. So I'm going to kind of preload it a little bit here to fit it into the machine. So that load that's on it now is still in the bridge, but we'll probably add more to it before it actually breaks. There we go. Yeah, I think that's, there it goes. All right. Okay, so 6.9, again, it's disqualified. So good design. I see you were putting together a great design, great detail. But the height became a problem. So sorry about that.
Okay, now next students are Olalde, Hessi, and Haley. This is also disqualified.
Again, because of the height, eh?
Yeah, height.
Oh my goodness. I'm sorry about this, guys. But to make it fair and consistent, everyone has to follow the exact same rules and same criteria. Again, understanding that the bigger, the taller something is, the more load it could theoretically carry. So that extra height may give it an advantage. All right, interesting how this is failing. Oh my goodness. I think that's maximum carry, but take note all the interesting layers that they built it in and then glued the layers together. But again, take note that they're kind of falling apart. So every place that the joints are, pieces touch, add more glue, and that could make quite a difference in this design. As real engineers, as a structural engineer, what we do is we simulate, build models, perhaps in computers, and we do the exact same thing. We load them and see where they fail. We learn how to build them a little bit stronger. In each iteration of design, we optimize, just like you guys are doing here, what works best.
Okay, next students are Caitlin, Alex, and Ryan. This bridge is also disqualified because it's short.
Okay. So, well, it is, we can set it on the edges a little bit here. So I would suggest that it's not necessarily disqualified, but I'm thinking, I guess we have a mechanism to measure them, and it must be just a little short. But we're going to test it anyways. See what we can do. But I think what's going to happen is the ends are going to break. So again, what I'm going to do is 3.8 is the official load, even though it's disqualified. But we're going to still keep testing it and see if we can get even more out of it to give an understanding of great design and what this design could do if it would have met the specifications. All right, very good. So there you go. We'll record that load, but as I say, it's not going to be a bridge that's going to be eligible for prizes.
Okay, now next student is Shante. Here is the bridge. This is also disqualified. Oh, sorry.
It is disqualified?
Yep.
Okay. And it's the
Dog.
It's the height. Okay. Yeah. In this case, it's the height again. Okay. So let's see what we can do here. Still need to get it. Touch the end. And I see the end kind of broke off here, and I don't know. I'll try resetting it. Being that it's disqualified, I think 4.8 is the best load we're ever going to get out of it. I don't think, because the end is kind of broken already. It doesn't really, at this point here, it doesn't really fit on the machine anymore. So we'll see what we can do. And you can see the tip doesn't really line up with the load. It's a little off center, but that's the best we can do. Okay, now I've created pieces. Okay, so good design, good job. Again, just making sure that it is built according to the specifications.
Now next student is Jamia. This bridge is also disqualified. It's a top.
Too tall again. Okay, wow. Okay, well, we'll just keep testing these. I'm sorry, guys, that well, we've got a little concern with the dimensions. You know, and I think great design. I like the pieces, very nicely made and very nicely sort of integrated in the middle of one another. So it looks like a great design. I would suggest, obviously because of the dimensions, that's something that could be done differently next time, but also in the joint areas and so forth. Again, lots of glue. That's a very important area to make the bridge as strong as possible.
Now, next students are David and Sam. This bridge is also disqualified. Sorry, it's tall.
Okay, it's too tall again.
Yeah.
Oh my goodness. All right. Okay, here we go. Looks like a great design. It's meant to reset it. Let's see if we get some more out of it. I think it is crushed. Okay, 5.5. All right. How's things going? Any comments? Maybe this issue of being too high and so forth, please just add a comment and we can give you some answers if you like, just to understand that a little better if there's a concern. Just a second. Next bridge is coming up shortly.
Okay, now this is Mohammed and Trust.
Okay.
This is tall.
This is disqualified again because of its height. Okay. But I like the design, the concept looks great. Let's see what I compare. All right, 4.5. Great design. Thank you.
Really sorry for that one. That was for student Anthony and Nathan. That
last
bridge
one.
was, yeah, the last one. Sorry.
Okay, good.
Yeah,
yes,
the same is disqualified because it's tall.
Okay, good.
Now next students are Eden, Karima, Lloyd, and Tormate. Yeah, this is disqualified again. It's tall.
Oh dear. Okay. Well, hopefully we can get it into the machine. I don't know. Okay, well, it's partly broken, but I do see some load there. So we'll see how much more we can take. And I'm thinking that, you know, it's kind of all coming apart. Again, great design. Again, glue. Obviously, we don't want things to be, you know, sort of easily falling apart like that. So lots of glue in the joints. For next time.
Okay, now next student is Avale, and this is also disqualified.
Again, because of the height, it's too tall. Okay. Okay, here we go. Actually, pretty good in the design. All right, 11 kilograms. Excellent. Very good job.
Now next student is Jaime. This is also disqualified. So sorry, it's tall.
Oh no. Okay. All right, here we go. I'm feeling pretty strong. Look at that. 12.3. So great design. I really like, again, how everything is kind of interlaid. Very good design, very good connection. Maybe a little more glue. It would be very good. Great design.
Now next students are Jason and Jack, and this is disqualified. It's tall. Sorry.
It's tall again.
Yeah.
Okay. Okay, well, we'll see what we can do here. There's going to be a few pieces at the top here I think are going to get crushed a bit, but we'll keep, there we go. But we'll still keep testing it until it breaks more dramatically. I guess that's it. All right, so 7.6, pretty good. All right, nice concept, nice details. I see there's some glue, some good spots there. So great, good job.
Now the student name is Alexis, and this is also tall, so disqualified.
Okay, so obviously there's something consistent. And hopefully it's understood what may have been where the misunderstanding may have come from, but it would be important for next year for the students and the teachers to work together, make sure they understand the criteria. And we had some great designs. I'm sure you're learning something on how these bridges are breaking that you can use and implement next year to make your bridge a little stronger, seeing where it fails. So, all right, I think we got 10.1, that's pretty good. And again, I see great design, great things, good design.
Okay, that was our last student for the school Victor H.L. White School. Thank you, everyone.
All right, thank you guys. Any questions? And I guess there'll be information sent to your classroom and some other videos and so forth talking about engineering and so forth. So great for you to be around. If you want to stay online and continue watching more bridges, that would be great. And we're going to take just a bit of a break here before we get set up for the next class. Okay, sure. Okay. In the meantime, while we're getting set up here, I'd just like to take note, give some background on what we're doing here today. There's 126 trusses to be broken today, built by 226 students, ranging from pre-K to grade 12. This is the final day of the 2023 competition. We broke bridges on Monday at Kilcolman Place Mall and yesterday at Bruce Middle School. By the end of today, we'll have tested 384 bridges and built by some 794 students. So, and there's a few teachers in there, I believe, too. This competition has been held since 1995, and this is its 29th year, and the third time it's been held virtually. As you can tell from my age, I was around in 1995 and helped us start getting this going. So great to see that it has lasted so long, and there's so many students, like 900 students being involved. So hopefully there's some out there that might tweak their interest in understanding what engineers are. That's our whole goal here, to help students explore what their interest might be and what they might consider as a career when they finish school. And the total, you can see in the background there, is 6,433 kilograms. So a great job for everyone to get that total amount added up to that. Yeah, okay, so are we ready?
We're just waiting for a school to join. So
okay.
If you and Vishali would like to talk a bit about your engineering journey.
Sure, okay. Come and talk about your journey.
Yep.
Just hang on a bit. The next class is still coming online, so we're going to wait just a bit for them to get set up. And in the meantime, my name is Don Spangolo, and this is...
Hi, I'm Vaishali. Hi, I'm right now electrical engineering intern here. Well, I did my electrical engineering from back home, India. I came here in 2019. I used to live in Saskatchewan, but nowadays I'm in Winnipeg, Manitoba since 2 years. Meanwhile, I applied for my license here in Engineer Geosciences, Manitoba, and I'm also evaluating my education here. And the thing is, now I'm volunteering here, so I can learn more about the Engineer Geosciences, Manitoba, how they are doing all these events. It's for all kids, and I also participated in Sunday's event. That's for kids. Actually, it was really nice. And now I'm doing this event with them too. So it's really it gives you too much really nice knowledge about I never ever attend this kind of event. So it's really great experience for me. Thank you for listening to me. And also, I apologize if I pronounce your names in the wrong way. I don't know, but yeah, sorry about that.
Great, great, yes. I'm actually a retired engineer. I work for Manitoba Hydro and other consultants as a structural engineer. Some of the structures, like the tented forks, the Gulf Dome structures, I was involved in the design. And as a professional engineer, you need someone to be responsible to ensure that these structures are built or designed. It doesn't matter if it's mechanical, electrical, or there's a variety of different types of engineers. We're responsible to make sure that we're protecting the public and building these things to ensure that it's safe for our society to use. And was there more? Yeah, sure. So we have some more engineers that are working in the background here, making this whole production work. So please go ahead.
Yes, so hi everyone, my name is C, and I hope you guys enjoy the Spaghetti Bridge so far. So I am a professional engineer as I am a biomedical engineer, so it's a little bit different from Don. So it's my job to kind of like assist doctors and nurses to help them build device and to help save lives. So it's the kind of focusing on the health of individual instead of like the public, but at the same time we do protect them and make sure that the device I create save lives. So yeah, it's
We're doing that in Manitoba. Right?
Yeah, that's right. Yeah, and then the great thing is that Manitoba is for like a few years ago when I started university, it's very different. It's not as a big biomedical hub, but now it's developing. So it's great to see the changes and great to see all the development that we're having.
Have to talk later. I have a daughter that's a surgeon. So.
Of course, yeah, it's good to hear. Yeah, yeah. So hope you all of you enjoy and have a great time.
All right.
Yeah.
Okay. And we have another engineer to talk about his background.
Hi, my name is Parker Williams. I've been a professional engineer for 2 years now. I just got it back in 2019. Before that, I was the EIT. I went through my schooling at University of Manitoba. I graduated from biosystems engineering, and I took a specialization in sustainable building structures. So it is civil, close to what Don is doing, but a little bit more specialized. So looking at green buildings, how to make them more environmentally friendly, so on and so forth. So,
sort of making use of existing recycled components to make new buildings.
Yeah, new buildings like that. Looking at green technologies, something like sun panels to be able to create electricity for the building, and other new technologies that come into the industry. But currently, right now, I'm working for a company called AGI. We do grain bins and agricultural facilities throughout the world. So that's my current line of work right now.
All right, good.
Yep, thank you.
Okay, and we have one more professional engineer to talk about his career. Take note, there's quite a variety of different types of engineering that is needed to make society safe. Go ahead, Gord.
Yeah, hello, I'm Gord Whitman. I'm an electrical engineer, so I work with a consulting firm in town, and I work on designing buildings, schools, airports, hospitals, and we really design everything from where the hydro comes into the building right down to the lights and plugs and how it all breaks down everywhere in between. But then I also do like fire alarm and voice data communications, security, all that fun stuff.
So again, as most engineering, it's kind of hidden in the background. In Gord's case, it's inside the walls and inside the ceilings where you don't really see it. But yet it takes all of those components to make a building work and be safe. Just like civil engineering, I can appreciate in going to school today, there's many different things that you have used and not necessarily knowing that there's been engineers in the background to make sure that it's safe and appropriate. When you flip a light switch, the expectation is the light comes on. But you can appreciate myself involved in designing hydro generating stations in the north, and all the electrical people designing the transmission towers and getting power from the river way up north to your light switch so that that light comes on. There is a ton of different components that have to be designed, have to be reliable, And even turning a tap, you expect water to come out. You expect potable water to come out, water that's safe to drink. Engineers design the mechanisms and the pipes to get it into your house. They are chemical engineers that make sure the water treatment provides safe water that's safe for you to use. Even walking down the sidewalk, engineers get involved and design literally the sidewalk, the roads, the bridges, various things. So, all right. And so we have one more professional engineer to talk about his background.
Hello, everybody. My name is Richard. I'm basically in a mixture of mechanical engineer and electrical engineer. I'm working in the wastewater treatment. So every time you flush the toilet, all the wastewater stuff goes to the pipe, which is just downstairs, goes to all the pumps and come to the wastewater treatment plant, like it being treated by the biological treatment process or chemical treatment process. They can be, take all the solid stuff out, nutrient out before they release to the river to protect the environment. So that's quite fun, control all the pumps, valves, chemical dosing, oxygen supplies. It's all part of the treatment process.
Again, it's something that happens someplace that people don't see, but yet it's very important to make our rivers safe.
Yeah, somebody working on the other end of the toilet. So.
All right, good then. Okay, so I understand that the class has now online, and welcome. And I don't know if you heard a little bit of the introductions or not, but my name is Don Spangle. I'm a professional engineer, and I've been breaking spaghetti bridges for a number of years, since 1995. And this year is the second year that we're doing this virtually. We've been in malls, we've been in other schools this week. And you can see that number of 6,433. That is the accumulative number of kilograms of load that all the bridges we've tested over this last week, including bridges built by almost 800 students. We are breaking bridges made from spaghetti, and to offset this spaghetti that perhaps cannot be used for food is based on the number of kilograms that you guys are building your bridges to be able to hold. We are contributing to Manitoba Harvest to offset the needs of others, and they will use the funds to purchase food on our behalf and distribute to those in need. So welcome, thank you today.
Okay, now we have Manitoba.
Maybe this is a new group, so
I will.
Give a little bit of background.
Okay.
Introduce yourself.
Sure. My name is Vaishali. I'm an electrical engineer intern here. Okay, and I'm today is the helper for Don. Okay, now the school name is Manitoba School. We have only one student for this, and the name of the student is Joel.
All right, all right. So it's Joel.
Joel.
Is Joel online and watching?
Yes.
Even though he's from one
His
school.
whole class is watching.
This whole class is watching. All right. So this is pretty special. And okay, Joel, let's look at the Great Bridge. Looks very, very nice. Very. I could almost say, if you've ever been to the ice cream place near the bridge, bridge drive-in, it may look very similar to this. So this is a very classic design that's been around for a long time. So, but we've made this one out of spaghetti, so we'll see how it goes, see how it carries. Great design. All right. I hear lots of crushing. Oh, wow. Look at that. 8.8 kilograms. Excellent job. Pretty cool. Very nice. And you can see how it kind of pulled apart, taking out where the failure points are, and maybe designing a bridge next year, Joel. You can see where to make things a little stronger. All right. Great design.
Of us here at Harvest Manitoba, I want to thank all of the participants in this year's Spaghetti Bridge Challenge. Harvest Manitoba relies on thousands of people all across this province to provide us with the food, the volunteer labor, and the funds that allow us to feed over 80,000 people each and every month. I congratulate you on what you're doing, raising awareness and money to support the work of Harvest Manitoba. To all of the contestants in this year's Spaghetti Bridge Challenge, good luck and thank you.
Hello, welcome everyone this morning. I'm here to break some more bridges. My name is Don Spanglo. We're going to be using this machine, and here's going to be the weight that the bridge are going to be able to carry. And we'll get started very shortly, but I'd like to introduce.
Hi, good morning everyone. I am Vaishali. I am an electrical engineer here, and today my role is I'm going to help them.
All right, okay. So as engineers, we are kind of demonstrating how to build a bridge and give you an opportunity, just like an engineer, to put some thought and ingenuity into designing a bridge. And to make it even more exciting, not just building it, but to be able to test it to see how much it carries. Take note, the 6,442 kilograms noted in the background, that is the total number of kilograms that all the bridges that we've broken this week have added up to. And we're going to be using this figure to provide a donation to Manitoba Harvest for them to be able to buy food product for those in need. So even though we're kind of making use of some spaghetti in a non-nutritional way, we are offsetting that by trying to help out others in need through Manitoba Harvest. So I'll explain things a little bit more in detail as we go along, and as we look at different bridges, I'll give you some hints on how to build a maybe better bridge next time, and let's go.
Okay, we are going to start with Amber Trails Community School.
And this is class Scott, teacher Scott, so welcome. And we are just going to...
Okay. Students' names are Astin, Uday, Jagjot, Marco.
All right, okay, here we go. And so I'll give everyone a job. Every time I test a bridge, this is going to hold the load from the last bridge, but I have to zero it to make sure we start the next bridge. So if someone sees that I'm not canceling and getting it back to 0.0, please shout out. All right, so this device lifts the bridge and pushes it against the bar at the top, and you'll see the numbers come up with the load in kilograms that the bridge is holding. Oh, all right, here we go. 3.0 kilograms. Great design. I see triangles, so that's a great solution for structural integrity. All right.
Okay, now next students are Gunmin and Jeremy. And this is the bridge.
All right. Okay, here we go. And cancel it. So any questions, please throw a comment in. We can answer it as we go along. All right. I think that's the best we can do. 11.7. All right. Very good design. Look at that. And you can see how the pieces broke apart. So great concept.
Now our next students are Aidan and Saina, and this are bridge.
All right, here we go. Okay. This looks like a pretty unique bridge. Try to get it centered there and sitting on the supports properly. And I gotta zero it. All right, here we go. All right, 11.7, cool. Is that the same load as the last bridge? That's kind of cool to have two matching. Great design, awesome.
Okay, now our next students are Crisia and Ramos. Looks like really nice bridge they made.
All right,
Yeah.
ooh, wow,
Yeah.
yes. Very beautiful, a lot of work and effort, curved lines. It takes a lot of effort to me. I've built a few bridges, and every time I put some glue on a piece of spaghetti, it kind of warps, moves around. So they've got a great technique here in construction. So let's see how much it can carry. I'm too sad to break this one. It looks so beautiful. Oh dear, there we go. I can see it's a broken, what I would call in tension. Look at that. 8.9, great design and very good load. Excellent job, guys.
Our next students are Ikam and Lime. This is Reach.
All right, again, lots of triangles. Good to see. Makes for a very efficient structure. All right, any guesses how much this can carry? I think it's going to do pretty good. Look at that. All right. 14.5. Excellent. Very good job. And again, lots of triangles. Very good detail there. And you can see where it broke. All right.
Okay, for the next bridge, we have 4 students, Prabjot, Amber, Ralph, and Eliza.
All right. So some of the bridges are individual and some are in teams. So good to see. All right. So take note. You can see that the bridge has some depth and it has some structural elements coming down. And you can see, though, that they stop here. If this system was carried over and the ends of this, instead of being here, came and sat on top of the support, that might have made the bridge a little bit stronger. So we'll see what happens, and we'll watch to see where it breaks. If it breaks along right against the support here in this area where the bridge is quite thin, take note that by making this a little bit different and making this curve a little bit longer would make quite a difference, I think, in carrying the bridge. We'll see where it fails. Oh, just as I kind of thought, this end piece, the thinner section kind of broke off. So next time, great design, great concept, but just tweaking the dimensions a little bit could make quite a difference next time. Great job.
Okay, now our next students are Parnit and Amber, and this is the bridge.
All right, okay. Again, this is kind of the same concept I was talking about with the last bridge, of these thinner sections just before where the supports start. Great job. Oh, there we go. There we go. All right, 3.7, very good. Excellent job. With just a little tweak to how it's built can help maybe next time. So please consider that.
Okay, our next students are Harjot and Jason.
All right. Oh. Okay, here we go. It's a little bit different concepts than some of the others we've seen. It's kind of a flat, maybe it looks more like a bridge you can drive over. We'll see how the efficiency of this type of bridge works. 2.7, not bad. Very good. You can see how it broke apart. Again, there's some places maybe a little more glue could have maybe held things together a little bit better. All right.
Okay, our next students are Enzo and Manat. This is the bridge.
All right. Okay, good. Great concept. I can see lots of strength in the middle. Again, kind of like the other bridges where we're seeing near the ends where the bridge is not as thick. If this piece here was started at the beginning but sort of ended up over here on top of the support, that could make a difference. Because I suspect we're going to see it fail, not where all the support and structural weight is, but it's going to have a bit of a problem. Excuse me, a bit of a problem at the ends. So we'll see what happens. Yeah, you see that? So what I'm going to do is I'm going to call 1.3 as the official load as far as being eligible for prizes. But take note, in the design of this bridge braking system, we also added these little extra fins in the bottom to test bridges that maybe are a little too short. So to demonstrate, take note now that we see these elements come down and they set on this much shorter support. And being that I'm not using the same span as part of the specifications, this load that I'm going to load it to is not going to be part of the competition because it's unfair because it has to span less of a distance. So you'd expect the bridge to carry more and not be consistent with other bridges. So just a second, I have to reset the machine. And to be curious for everyone, as to what it may be able to hold, in this configuration where these supports come down and sit directly on a support. And we'll see how much more it can carry. So quite a bit more. So that kind of demonstrates in getting these supports here coming down directly on top of the support like this, instead of over here having a very thin element that lasts a little bit. So hopefully you can understand that and make your bridge much better next time.
Okay, so now this is our last bridge of Amber Trail Community School. Student names are Patrick and Gunnar.
All right, so this is teacher Scott. All right, very good design. I see triangles. I see an element in the middle here where the support is going to come down on. I see these triangle sections here coming down and bearing directly on the support. So it looks like a very good design. And we're going to see how much load it can take. We got it 0. All right. And what I'm seeing here is obviously this piece here where it was glued to the bottom kind of broke away. So maybe more glue in a place like that could make quite a difference. But you can see how differently it failed. So very good design. Excellent job, and 7.1 kilograms is pretty good. Okay, are we off? Okay. Oh, okay, good. All right, so next class.
Next school is Never Valley Elementary School. And
Niverville. All right,
Yeah.
Welcome, Niverville. So hi, if you've just come online, I'd like to introduce myself. I'm Don Spanglo. I'm a civil engineer, and we are providing this competition to give you an opportunity to learn about engineering and to use some ingenuity to design a bridge and to kind of follow through what an engineer actually does in designing a real bridge that you may drive over. And obviously, it's fun to build them, but I think it's even more fun to watch them be tested and see how much actual load they can take.
okay, hi everyone. I'm Vaishali. I'm an electrical engineer intern here, and today I'm the help of Don.
Okay, all right.
So now the first student are Brian and Hyder.
Okay. Take note, the number behind me, 6,509, is the kilograms that all the bridge we've tested this year, which is built by some 800 students, have carried. And what we're doing is we're using this number to provide a donation to Manitoba Harvest for them to provide food for the needy. I guess we are kind of using a food product here, so we're trying to offset what we're doing and using this as a demonstration to help Olympic Harvest provide for the needy. So I speculate the bridge is supposed to work like this and maybe not like that. So I'm going to set it up like this. And take note that it's got a lot of strength and support in the middle. And I'm seeing as it gets towards the ends of the support, it's not quite as thick. So my concern is that when we test it, we may notice the bridge breaking, maybe not where you think it might break, but we'll try it anyways. And look at that, it's not breaking where I thought it was going to break. All right, very good. 3.1 kilograms, so a very unique and interesting structure. So thank you for trying. Thank you for building, actually, not just trying, but great for you to put the effort in.
Okay, now our next students are Aubrey, Nora, and Lil. And this bridge is disqualified because it's short. Sorry about that.
Okay, so we're going to try to test it anyways, and what may happen is the ends may not be sitting fully on the structure. Again, something to watch for when you're designing the bridge is to follow the specifications and make sure that it is long enough. So being that it's disqualified, it will not be eligible for prize winning, but we're still going to test it and see how much the design can be. And I've got to zero it. Thank you, guys. All right, here we go. All right, very good. Look at that, eh? So if it was just a little bit longer, that would have been a very good load to potentially win a prize. So, but hopefully next time you understand the criteria. But excellent design. Look at that, 20.7. Very good.
Now our next students are Victor, Dinah, and Karan. The bridge.
All right. Okay, just need to adjust this a little bit. Okay, that's zero. And here we go. Let's see what this design can handle. So we're questioning a little bit, but I still think it's going to hold more of it. Oh, there. Oh, look at that. 7.1. Excellent. All right. Good job, guys.
Okay, our next students are Michael and Omar. And this is the bridge tonight.
All right. Okay. So I'm assuming that it's going to be loaded like this. I don't know if it was intended like this or not. I don't know if there's time to get any feedback, as if they want the bridge to sit like this or sit like that. I'll maybe just take a moment or two and see if we can maybe respond to make sure. Do you want it horizontal or vertical? I'm not quite able to understand the concept, so best try to get it from the designers themselves.
Sitting up.
Like this. Okay, perfect. Okay, good. Thank you for letting us know.
Yes.
Okay, I'm going to switch my hands around here. Here we go. Uh-oh. Oh, there we go. 5.6. Very good. All right. I see. Interesting. They got a bit of a truss mechanism going there and some reinforcement here. Very good. I could suggest that maybe at the ends where it actually broke, if there was some more structure that came right out and sat right on top of the support, the bridge may have held even a little bit more. But this is a very good job.
Okay, our next students are On, Kaiden, and Pala.
All right. Okay. Now, I'm pretty sure the bridge is intended for this, so I don't think I need to confirm what it is. Hopefully the designers agree. All right, here we go. Take note, I like to have this bar here perpendicular to the bridge. That's consistent to all bridges. It might give a disadvantage to some. It's another. Wow. Explosion. All right, very good. 5.8 kilograms. Excellent job. Thank you.
Okay, now our next students are people. And this is Rich.
All right. Okay. All right. Here we go. Again, I've kind of talked about, getting some of these members to sit directly on top of the supports on each side. This piece here may or may not be where it fails, but we're gonna watch for that. Oh, all right, there we go. 8.4. Very good. Good design. Another explosive failure. It's much appreciate you guys building these things, knowing that they're going to be crushed. So, but I think that's the fun part.
Okay, our next students are Queen and Janet.
All right, here we go. A little bit of crushing at the end, but I think we'll still keep testing it to see if we can get a little more, but I'm going to help support it a bit. And I think what we're doing is we're crushing the ends at 7.2. Excellent, very good, guys. It's always fun to see them explode.
Okay, our next students are Friendly, Grayson, and Bennett.
Okay, so I've kind of mentioned some concepts here in this type of a bridge, so we'll keep testing and see. I'm forgetting. Thanks, guys. Okay, here we go. Look at that. You see the end kind of broke off there. So we've talked about that before. So 7.8 is still very good. So excellent job, guys.
Our next student is Johnny. Unfortunately, this is disqualified as the bridge is tall.
Okay, so again, we kind of had one like this before. And I believe the concept was to be vertical like this. So I'm going to take it as if this is how they intended for it to be used as well. Okay, so we'll see what we can do here. This looks like a very sturdy bridge. Lots of spaghetti. And let's see how it fails. Oh, the ends are coming apart. That's it. Yeah, 6.2. So pretty good design. All right, very good.
Okay, so our next students are Sarah, Charlie, and Cassie.
All right, okay, so I believe the bridge is supposed to be sitting like this. Is that right? Okay, any guesses? We've seen a few bridges kind of like this. So maybe you guys got some ideas of what you think it might be able to. Uh-oh. I think it lost a fairly significant component. I think that's about it. Oh dear. So I think this is the piece. So again, maybe providing a little more glue to hold all the pieces together. Glue at the joints is very important. So maybe that might make your bridge stronger next time.
Okay, now this is the last student of the school, Nerville Elementary School, and the person name is Eddie.
This is the teachers, Mr. Walker.
Mr. Walker, hi, Mr. Walker. So yes, we're going to test your bridge, and you've maybe understood some of the concepts that I've talked about, and some bridges that kind of look similar to this. So we're going to test it, and we'll see where it's going to fail. And maybe next year you can build another one and learn as to how this would fail make your next bridge even better, which is typically what a real engineer does. They design things, maybe not building models like this, but in computers to figure out what is more efficient when they're designing a bridge or a structural element. And they figure out where the mode of failure is, and then they learn to make it a little stronger in that area. And through iterations, make something very strong and efficient. We'll see how strong and efficient this bridge is. And kind of what I talked about, kind of the end breaking off there, but 9.4, all right, pretty good. Good for you to try and to work with the students. So hopefully you can learn from them and they learn from you. All right, very good. So we're starting a different school now, and
Yes,
have you know if they've been online or not? Okay, so I'd like to introduce myself. I'm Don Spangler. I'm a professional engineer. I'm a civil engineer, structural engineer, and I'm here today to operate this machine, to test, to see how much load your bridge can carry. And I have a
Okay.
help.
Yeah.
Yes.
Hello, I'm Vaishali. I'm an electrical engineer intern here, and today I'm going to help Dawn for announce the student's name. So we are going to announce the school name is Amber Trails Community School. Welcome everyone.
Welcome. Yes. Okay. Just like to make note that the number of 6,596 behind me, that's the number of kilograms that all the bridges that we've tested today that have been built by some 800 students. That's the total load that they've all carried. And what we're doing is we're going to be converting that into a donation to Manitoba Harvest to help with providing food for needy people. All right, so enjoy. Any questions, please make them in comments, and we'll get started.
Okay. Our first students are Carmela and Aubrey.
So I see a number of bridges in the class that have kind of a dished shape like this. And I don't know if it's going to make any difference or not, but I'm kind of curious if they could quickly send us a comment for all these bridges to see if they should be sitting like this or they should be sitting like that, upside down or right side. So just I'll give you a second to please respond. I want to make sure that I test them in the condition that you were assuming. So bear with me. So as a structural engineer, they design structures. This testing machine is kind of a structure, and which I designed specifically for breaking bridges. So, there's also electronics inside. This little device here is a load cell that sends a signal through this cable into this box, and it has a readout. So this is kind of a demonstration in itself of what engineers might do. All right, so my understanding is we set them in this position, and I'm assuming that's the case for these other bridges that have kind of a similar shape. No problem. We will just adjust our machine accordingly. All right, here we go. Let's see what we can do. I think that's filled for 6.2. All right, very good, guys. A very unique design, so great to see. And we'll see how that compares to other students in your class now.
So Don, the class is apparently having quite the debate about which way round is best. So they would like you to choose as a civil engineer. So your decision.
Oh, I gotcha. Okay. So, sure, I will talk about various shapes and we'll introduce the next bridge here.
Yeah, the next bridge is Manbridge.
Okay. As a structural engineer, maybe you've walked across a little bridge across a brook or a little creek and you kind of walk over a hump. And that has kind of two functions. One, it makes sure that there's clearance for water to run underneath it, but also having something designed like this, depending on how the loads are distributed through it. I believe in this position, I I believe this position here would be a little bit, not much, but a little bit more efficient, but pretty hard to tell because it also depends on the thickness. What happens in this area here? How much spaghetti is in the bottom of this compared to how much is in the top? There's a number of varieties, but I would say this is probably the better orientation to consider. Now, the last one we made, I'm saying I don't know how much difference it really makes, but I will suggest that we test the remainder in this position. That may or may not make that much of a difference. I do know when these fail, they're just going to kind of fall apart. There we go. 5.9. Very good. Excellent. All right. Unique design. Very good. And yeah, we have a few more to test that look like they're all very similar. So
Yes, this is Elijah and Jackson.
all right. So it seems like as a whole class, you kind of got together and you had some ideas of how things should work, and you built some bridges that look kind of similar, which is awesome, which is good. But I believe there's a couple others that look a little different, so we'll try out them. And I'm sure you've seen maybe other bridges. I don't know if you're online to see the last school we had to see different types of bridges and how much load they can carry. All right, here we go. 13.9. All right, very good. You guys may have a good theme going here in the types of designs that you've come up with.
Next is Pratap and Prince.
All right, so this one you see is a little different and a little unique. My concern is you can see how, and this is a problem when you're gluing spaghetti together, there's moisture in the glue and it likes to warp the spaghetti, so you can appreciate it's hard to hold it straight. I've tried to build bridges myself and I've come across the same kind of problem. I'm sure this would work a lot better if this A-frame was nice and straight and not kind of leaning over like this. So we'll try to test it, and I'm going to sort of compensate a little bit here. And I believe it's supposed to be loaded. It's supposed to be loaded in the middle like this. So we'll see what happens. Oh, here. So 3.6, I would consider that the bridge is failed, but as a demonstration, I'm going to try something different. So 3.6 will be for your, I believe, the way the bridge was supposed to be loaded, and you can see a pretty major component has broken. But we still have the bottom part that looks kind of similar to the last two bridges that we built. And what I'm going to consider, just as an example, is I'm going to flip this around like this, and we probably are not going to get any more load out of it. But I'm just curious. So this is going to be an unofficial load. Take that, please. This will not get you a prize if it gets any more than 3.6, but it might not. We'll see. Doesn't look like, oops, cracking. Yeah, so no, we're not getting any more out of it, but it did crack right in the middle. All right. So we tried, but I guess that didn't really help.
Next turns Mohammed and Sam. This is the bridge.
Okay. All right. So it looks like similar to some of the ones, except this one's straight. It doesn't have that little bit of a curve to it. And we'll see how much difference this makes. Again, it's kind of hard to tell, you know. So I think it's best this way. Lots of structure in the middle, very good. But you see at the ends, near the supports, the load has to, you can appreciate, the load has to transfer from here and it has to get over to the supports here. But we do see lots of strength here because of the thickness and the amount of pieces of spaghetti. But as I get near the ends, near the support, there's less spaghetti there. So I'm a little concerned as to where it's going to fail. If the same amount of spaghetti was made bridge longer and all this came out past the supports, it would make a difference. And yeah, I'm kind kind of failed at the ends there, so that's about what we were left with. Now, okay, so sorry, that's about all of you. 2.6 is still pretty good though. Next time, hopefully give you some hints to make it even better, that you understand. If you don't, please make a comment and we can answer any questions you may have. We'd be very willing to try to help you build the strongest bridge possible.
This student is Andrit.
Okay, so we're going to go with this curved in this direction. And see what we get. All right, cool. 17.7, excellent. That's very good. Good concept. And it looks similar shape, but I could feel that there's enough pieces at the ends, and there was lots of glue to hold it together, and I think that might have made a bit of a difference, having lots of glue.
Okay, now our next student is Ekanveer.
Okay, now I do see a section here is flat, so I'm going to assume that that goes on the support like that, and we're going to test it in this configuration. Just a second here. Okay, here we go. Ooh. Look at that. Wow, okay. 26.8, excellent. Very good. And I see lots of glue, and I think that made quite a difference. It's a good solid structure, so good to see. And I guess that's probably the highest load we've had so far in this class. So good for you guys.
Okay, now our next student is Sharanjit, and this is great.
Okay, wait a minute. So this is very similar to one we had before too, where again, this upper triangle-shaped piece, it seems to have gone a little bit off to one side, which may not help its structural integrity, but we'll try our best to see what we can do here. I'm going to help twist it a little bit to see if we can get that upper section to work a little better. But I think what's going to happen is you're not going to get any more load than that. So I'll have to say at this point that the bridge is even though pieces haven't completely broken, well, actually I do see some cracks right here too. I can get the camera focused there. So I guess at this point in time, I'd call it the bridge has failed. 1.7. A good design, interesting design. Hopefully, I've tested it in the right orientation that you like. But yes, you can see by getting these pieces maybe more vertical and in line could make the bridge a little more efficient. So, great job. Thanks for coming out.
Okay, now our next student is Samro, and this is the bridge.
Okay, thank you. Yeah. And we're going to do this same orientation. Okay, there could be some crunching at the ends, I see, but I think we'll allow a few little pieces at the ends to kind of crush to the point where the whole thing collapses, which I guess it's doing now. So I think is the numbers going up? I think that's it. No, that's it. Yeah. It is, a lot of pieces have failed, you can see in here, so I don't think we can get any more out of it. It's the best we can do. So 8.5. All right. Good design.
Okay, now our next bridge is made by Naya.
All right. Okay, just a couple more to go for this class. All right. And again, we're going to just test it the way we've similarly done, and probably be some crushing initially, but we'll keep testing until it completely breaks. I'm going to reset it a bit. I'm going to just move it over a bit this way. All right. And keep testing it. see what we get out of it. There's lots of crunching, and I think that's it. So 9.2, very good, excellent. All right.
Okay, so our next student is Annabella. This bridge is not qualified, it's short, sorry.
It's short, right? Yeah. So yeah, we could test it. I will try to test it anyways in this configuration. Right, but there's just a couple of pieces of spaghetti at each end that is actually sitting on the support. So again, it should be just a little bit longer, and I think the bridge would have been somewhat stronger. But we'll see what it can carry, even with those last two pieces. But again, this is disqualified. So there it has failed officially. So 4.1 is the official load, and I don't know if we can fit it. So yeah, no, I think that's the best we can do. So sorry about that being a little bit short, but again, you've seen some of the others that have been a little bit longer, and maybe they've carried a little bit of load. So something to consider for your next bridge. All right, very good.
Okay, so now we are all done with students of Amber Trails. Now this is the bridge made by teacher Kaira, Mrs. Kaira.
All right. Okay. All right. Good to see you, teacher. Now I see a little loose piece here, which I don't think is going to help, but it may hinder how I load it. So I'm just going to kind of let it kind of sit in there. And great to see teachers involved too. All right. What happened if the students' bridges carry more than the teacher's bridge? I'll let the teacher and the students discuss that. But anyways, kind of fun to see a teacher involved too. All right, good for you. I think even the teacher may learn from watching other bridges being built so that they can build a strong bridge next year. All right, here we go. I think it's broken. All right, look at that. 26.1, so that's pretty good. Excellent job. A good design concept. So hope you had fun doing it. So excellent. Good for you to be involved. Okay. So okay. So good. So we have a few more bridges to break. And this is from?
Okay, now this is from Erickson College Institute.
All right, good. So welcome to our bridge building and breaking competition. My name is Don Spangle. I'm a professional engineer, and I'm going to use this device machine here to test your bridges, break your bridges, and the readout at the top here will be the maximum load that it carries. And we're here today to demonstrate to students what engineering is about, and hopefully building bridges gives you an opportunity to be an engineer while designing your bridge. And the fun part is to be able to see it to be broken and to see what kind of results your design comes out at.
Okay, hi, I'm Vaishali. I'm an electrical engineering intern in Engineer Geoscientist Manitoba. Today I'm here to help Don. So now we are going to announce the name of the student, the first student of Erickson College. Welcome everyone. Surar Ajni.
Take note of the number behind me, the 6,722.
Yeah, it's the bridge of Suraj.
Okay, thank you. That number represents the total weight that all the bridges we've tested this week. And we are going to be using this number, adding up all the loads that you guys have designed your bridges to carry, to donate to Manitoba Harvest to help them provide food for the needy. All right, here we go. Any questions? Please make a comment online as we go through this. This looks like a great bridge. It's nice and tall. It comes over the supports, great. It has lots of triangles, great concepts. Making it structurally sound. And there we go. All right, 12.6 kilograms. Excellent design. That's very classic for a bridge. Great.
Okay, now our next student is Dylan. This is really pretty design.
Yes, very nice. Excellent design. Definitely, it sits on the supports good. It looks like it's lots of triangles. The one comment that I will make is that as per our rules, is that the bridge is going to be loaded in the middle. And take note, we have lots of neat structures and so forth. But right where the load is coming down, we have a member that spans across here. I could suggest that if there was one of these members that came to this point and triangulated where all the load's going to be added, that may make the bridge a little bit stronger. So I'm going to watch to see where the mode of failure is. What piece is going to fail first? And when you design your bridge next year, take note of how maybe to add some more members directly under the middle, how it could potentially make it that much stronger. So you see it's kind of breaking right there, but yet the rest of the structure really isn't loaded. So 3.1 is the official load for it to fail, but I'm just going to keep crushing it and see what happens. See if the rest of the structure can pick up and you can make that load go higher. And it doesn't look like we can. So there we go. So maybe that piece across there didn't make that much difference, but it's worth a try. We'll see. Maybe you can experiment a bit for next time.
Okay, now our next student is Amanda. I'm really sorry your bridge is disqualified. It's a little bit tall.
It's a little tall. Okay. It looks like a great bridge, though. So again, the intent is to be able to follow the specifications, the instructions. We want to keep all the bridges consistent so that everyone has a fair chance of winning the competition. And take note that a bridge that's extra tall actually makes it more efficient and be able to carry more load. So that's why we put a limit on it. And since this bridge is a little higher, that could make it a little bit stronger, which is maybe unfair to others that have built a bridge that's lower and within the specifications. So by all means, we're going to test it, see what it can carry. And I could say next time when you build a bridge, to make sure that you follow the rules and make sure you don't get the bridge too high. So this looks like an excellent bridge, and it might prove to be a great strong bridge. There we go. 9.1, very good, excellent. So height is something to watch for next time. Thank you very much. But great design.
Our next students are Magnus, Gina, and Lena.
All right.
Nice design.
Nice design, and it's a real bridge. Like you could drive over it. They created a road there or a walking bridge, so it's a pretty neat design. So it mimics a real bridge. Whereas some of these other bridges, it's more like a truss made to just support. This again is a unique concept, but let's try to see how much it can carry. Oh, such a beautiful bridge, and I'm just smashing it. All right, 2.2, pretty good. Excellent design. Very nice.
Now our next team is Matya, Avery, and Black. This is the bridge.
Just the second one.
Oh, yeah.
All right. Okay. So, not too sure how it is to be tested. I think because there's some components in the top, I would assume that that is the orientation that it should be in. Okay. All right, here we go. Any guesses? It breaks right in the middle. Cool, look at that. Eh? So 8.1. Very good. Great job, guys.
Okay, This is the last bridge of the school Exxon. Student names are Ozzy and Chase.
Great, okay. I'm gonna turn it around like this. Oh, yes. All right. Forgetting that. All right, good. Okay, here we go. Last bridge in your class. Oh, there we go. 1.5 kilograms. Actually, not bad. That's pretty good. I like your design. Kind of different and unique from others. Take note that it is flat, where some are taller. So that could make a bit of a difference too. So good design. All right, very good. All right, so I'd like to give you some idea of how things have been going this week. There's going to be 126 bridges broken today, virtually, built by some 225 Manitoba students from ranges K to grade 12. In this final day of the 2023 competition, we have broken on Monday at Kilboden Place Mall and yesterday at Bruce Middle School. And by the end of today, we'll have tested some 384 bridges. That's what's adding up to that 6,759 kilograms. All right. And some 794 students have been involved, with a few teachers too, so great numbers. Great that we can sort of connect to that number of students to give them an idea of what engineering is about. This competition has been held annually since 1995, and this is our 29th year of running this. So hopefully others like yourselves continue year after year, and we can continue our introduction of engineering to students. The stronger the trust, the more money Engineers Geoscientists Manitoba are donating to Manitoba Harvest, as I've explained about the 6,750 some kilograms there. Just to give you some idea of some of the strongest bridge in past years, last year, 2022, which was done virtually just like this, 172 kilograms from a grade 7 student from Bruce Middle School. In 2021, 140 kilograms from a grade 4 student from Dr. Hamilton School. 1920. 176 kilograms from, again, a grade 5 students from Dr. Hamilton School. John Taylor Collegiate in 2019 had a bridge that carried 180 kilograms from a grade 12 student. École Rivière Ruth in 2018, 195 kilograms from a grade 3 student. Oh my goodness, that's pretty good. 2017, grade 10 student from Shaftesbury, 192.7 kilograms. So some pretty awesome loads. Don't know what the maximum load is in the week. This week has been. I don't know if someone can look that up and provide us. Then we're going to be back from lunch at 12:30, and you can continue watching if you like. We'll have some more classes joining us, but if you want to learn more and see more bridges being broken, please come back online at 12:30. All right. Okay, bye for now. Have a good lunch.
From all of us here at Harvest Manitoba, I want to thank all of the participants in this year's Spaghetti Bridge Challenge. Harvest Manitoba relies on thousands of people all across this province to provide us with the food, the volunteer labor, and the funds that allow us to feed over 80,000 people each and every month. I congratulate you on what you're doing, raising awareness and money to support the work of Harvest Manitoba. To all of the contestants in this year's Spaghetti Bridge Challenge, good luck and thank you.
Hello, everyone. Thank you for joining us to continue our breaking of spaghetti bridges. It's been a great week, and we have a few more bridges to break here. I'd like to introduce myself. I'm Don Spangelo. I'm a professional engineer. I've been involved with the association for many years as a structural engineer. and that is designing buildings that support structures, designing transmission towers, and involved Manitoba Hydro, building hydroelectric dams. And today helping me is...
Yes, my name is C, and I am a biomedical company working for Copen Technology Canada. Yeah, so I will be down system today, and then we will start working some bridges.
All right, good. So an introduction, you see a number of that 6,759 behind us. That is the total loads of all the bridges that we're breaking today have accumulated up to that weight. And we're going to be using this to base giving a donation to Manitoba Harvest to help needy people, and kind of connected to, obviously we are using spaghetti here that is not really being able to be used for food. So we're trying to offset that functionality in this fashion. And yes, we'll talk about each bridge a little bit, give some hints along the way to make your bridge maybe a little better next time. And hopefully that will help you understand what engineering is about. Engineering is trying to optimize various components of engineering related items, which are all intent to protect the public. That is our goal. When we design a bridge, we design a building, we as engineers are assigned to be responsible for the design to make sure that it is being done that's safe for the public and it doesn't harm them. But today we're going to be breaking bridges, which I guess it's the ultimate test to see how good a design is. So sorry for breaking your bridges, but that is the ultimate way to determine how good they are. So there's a readout here, and as we add our bridge to this, we're going to jack the bridge against this load cell, and that will increase the numbers, and that will indicate to us the loads the bridge will broke at. All right, okay, so to start with, which school are we working with now?
Yes, so I have St. Catherine Homeschooling Group today. Yes, so the first bridge I have here is with Rachel, Jacob, and Henry. Unfortunately, you guys have been disqualified because the bridge is too short.
Okay.
Yeah.
Okay, so talk a little bit about disqualifications. To make it as fair as possible, obviously, if a bridge doesn't have to span as far, or if a bridge is made taller, these are aspects that maybe makes the bridge much more stronger. So the intent is to keep the bridges within a certain parameter, so it is a fair judge comparing one bridge to the next to see who qualifies for the prizes. So we do have some limitations in the instructions that are given out by the association. Dimensions, the height, the length, the weight as well are all defined, and the intent is to stay within these parameters. Just like a real engineer, we have certain criteria that we have to design and build around. So being too short, it kind of still sits on the supports, but it is not quite long enough to meet our criteria. So we're going to be able to test all of these bridges, but some of them that are disqualified, the load that they carry may not be used to qualify them for a potential prize for each classroom. So don't know how this bridge was intended to be supported, but as an engineer, I'm going to make a call to load it in this direction, because I think that might be a little bit of an advantage for it. And so I don't know if that was what you intended and when you're designing the bridge for it to be, but I'm going to make this call. And here we go. I'm going to operate the jack mechanism, and we're going to see at what load the bridge starts to fail. Oh, there we go. 1.9 kilograms. Actually very good. And this is a very unique structure. You see what they've done is it looks like they've crushed spaghetti, made a kind of a matrix. And I see there's some standard strands of spaghetti, but then there's also this matrix. So very unique, and obviously someone is trying something a little different. Not all the bridges will be like this, but it's great to see someone try to make something that may be a little more efficient, a little better than the next one. All right, here we go.
Perfect. The next one I have here is from Mason, Felix, and Samuel. Unfortunately, this one has been disqualified because it's too heavy.
Oh, there. Okay. Again, you can appreciate the more of something you use to build a structure, the heavier it is, the more material, the stronger it would be. So that's why we've, again, limited 350 grams is our criteria. Because it would not be fair to everyone if we had unlimited amount of weight that each bridge could carry. So unfortunately, and also I'm looking at the bridge here, I see great structures, I see lots of triangles, support structures, it looks really great as a bridge. But take note that at the very ends, it almost looks like the bridge should be a little longer to sit on the supports a little bit better. If these structural elements here came down on top of the support like this and everything was extended accordingly, you know, I bet the bridge would carry a lot more. My concern would be is that maybe all this great structure in the middle may not be utilized. And as you can appreciate, the intent is to get the load from the centerpiece, from this to the support. And it's got to go through this section here where the bridge is not as durable. So I'm concerned of where it might break, but we'll see. Yes, okay, thank you. I need to be reminded if I forget to change that.
I'll remind you.
Thank you. There we go. And watch where it fails. Just what I expected. See, the end broke off, and yet really the major part of the structure is not really being used yet. So what I'm going to do is, I'm sorry, I'm just going to break this off because that's pretty easy to break off. And so 3.2 is going to be the official load that it carried, even though that it is not eligible for a prize anyways. But I'm going to demonstrate by putting it on this lower section here, which again is a shorter span, makes it more efficient. But take note that the supports and the main structure components are sitting right on the support. So we're now curious as to how much extra it can carry. So this is just a case study to prove to people that if you build a bridge and have good support right over the supports, it can make quite a difference to the bridge. So let's see what it can carry now. All right, so definitely you can see the difference in the efficiency. So take note of that little clue to build your next bridge. All right.
Okay, thank you, Don. And for the next entry, we have Coraline from grade 7.
All right, excellent. Now this looks like a really good, strong structure. Notice the members have lots of glue on them, and they're big, heavy, beefy. It looks like it's designed the right span, the right height, and obviously below the 350 gram criteria. So be curious what happens here. I'm going to have to position a little bit. Take note, as I've tried to build bridges too, when you get spaghetti wet, it kind of, sometimes it works. So that's a little bit of a problem in how it's constructed. And I've had that same problem too. So I'm going to try to position the bridge here to optimize that slope. And see, this is a good, strong bridge. All right, all right. Excellent. Now, that's, obviously someone has great experience here, so good for you guys. And you know how to build it, maybe build it before, but look at the results. Beautiful. Now, I think it did hit the camera, but are we still okay? Is it,
You look good.
it's still good? Okay. All right. That's why I kind of stood back there to watch the thing. So excellent.
Perfect. And the next entry is from Brielle, kindergarten.
Kindergarten. Oh my goodness. All right. Great for you. Both were able to be watching. See what your bridge can take. This looks like a very good bridge. All right. Look at that. Excellent. Very good job. Lots of glue. All right. Very good.
Wonderful. And the next entry is from Mateo, grade 5.
All right. Okay. Let's make sure we get it all set up right here. Let's see what this bridge, a very basic A-frame, all right. Look at that, oh my goodness. Excellent job. So just a very basic A-frame can really do a lot. The pieces are glued together and are nice and round and very efficient. So great job. All right. Okay.
Yeah, wonderful. Thank you, Don. And sorry for getting this name wrong, but I think it's Eli. Yes. Eli. Yes, Eli.
Eli.
Yes.
Eli. So
you.
thank you, Eli. Great looking job here. Nice A-frame with some extra little pieces supplied. It looks like there's lots of glue in many places. So I'm very curious myself how well this is going to be. Looks like a good job. All right. Look at that. Excellent. 22.4. Very good.
Yeah, so the next one is from Angeline, grade 2.
Grade 2. Oh my goodness. Very good design. Hope you had fun building it. I'm sorry we have to break it now. Here we go. Oh, I'm going to reset it. I think we can get a little bit more of it. So if there's any questions, you're curious about what we're doing or why we have certain rules and why certain ones have been disqualified or something, please make a comment in the chat room and we'll be able to answer you right away. All right. Very good. 14.1. That's pretty good. Very nice.
And the next one we have is Cabral from grade 4.
All right. All right. Okay. So this is another little different design. It is just a very basic round element. And you'll see how it works. I'm just going to look and see. You know, it's probably the best orientation for it. All right, whoa, there we go. All right, 3.6, excellent.
Yes, and the last one is from Xavier, grade 8. Unfortunately, it's been disqualified because it's too heavy.
Oh dear, okay. Great design, but yes, again, obviously, if we don't limit the amount of weight of the bridge, you can obviously make any bridge stronger than another if you make use of more spaghetti and more glue. So that's why we have a limitation on the load, so that everyone has a fair chance at seeing how much their bridge carries compared to everyone else that all meet the same criteria. Oh my goodness, I can feel this one being good. Wow, very good. So too bad that it is a little heavy, definitely a great design. And I would say by doing exactly the same bridge, but just a few less pieces here and there to keep the weight down, it would have been a great competitor. So thank you for coming out and making your bridge.
Perfect. So the next one, we're moving on to the individual entries. The first one here I have is from Eva Zhang's first grade.
First grade, and what school?
Individual entry.
Oh, okay, so not connected to any school, but great for you to come out and learn about building bridges. Excellent. So I'm assuming this is the way it's supposed to carry a load, so we'll test it. All right. Good for you to get involved. And hopefully you're on. Hopefully you're able to be online too. Here we go. Oh, here we go. All right, 0.5. Not bad. Very good. Hopefully keep online and watch some of the other bridges and how they're made. And you've got a number of years yet to compete, but maybe you can learn from some of the other bridges to make a bigger, better bridge next year.
And perfect. Here we have from Christopher, grade 2.
Grade 2. All right. Here we go. Okay, Christopher. Any predictions on how much it's going to carry? It looks like a great bridge. Very traditional A-frame and vertical pieces right underneath where the load is coming down. Looks like a great design. And all right, there we can see pieces breaking. 14.5, excellent, very good. Nice design.
Perfect. The last one we have is from Josh and Sam.
And they are watching online.
All right, oh, welcome, hi. All right, here's the fun part. I know it's a lot of effort to build one of these, you put a lot of time into it, and now I'm gonna crush it. So, but hopefully you don't mind, and I'm sure you're very curious of how much it's gonna carry. Again, great A-frame, great length, great height. So this will be an awesome bridge to see what it can carry. All right. Excellent, look at that. Oh my goodness. 23.2, excellent, very good. Great design, great concept. Yeah, I can't really say much more of what you could do a little bit better, but excellent, worked out very well.
Perfect, so I think we're moving on to, we're taking a little break right here. So it's a perfect opportunity for me and Dom to talk a little bit about what we're doing. So I can start first.
Sure.
So I am a biomedical engineer working with corporate technology. So I've been there for about 4 years. And since it first started, it's been a wonderful journey. I'm working on different devices that help, doctors and nurses to save lives. So if any of you are interested into becoming a biomedical engineer, it's a wonderful area to be in. You can start anywhere. You can start, if you're interested in math and science, just go with it. And then you can discover your passion from there.
Great.
Yeah.
I could sense some passion. Yes. I'm Don Spangolo. I'm a civil engineer involved in structural types of items. One thing in designing and building this frame here is to test bridges many years ago. But in my job, I'm typically involved in structures of what holds up a building, what holds up transmission towers, those things on the side of the road that the transmission lines span on. And also generating stations for Manitoba Hydro that are dam structures that hold back the water. Water runs through the units and we make electricity. So these structures are very important to our society, to providing us electricity and making it safe so that everyone below the dam can be safe and ensuring the water doesn't accidentally release more than it should. And to give an example of what engineers do in general is we design things, optimize things for society, and as a professional engineer, we're given the responsibility to protect the public in anything and everything we design. Of course, in the medical field, that could be very direct aspect of health. And for me, designing a bridge structure to ensure that it doesn't fail. There's many things that you have experienced and used today already that you don't realize, but engineers have been responsible to provide that to you to make our society safe. When you flip a switch, when you wake up in the morning, you expect a light to come on. I appreciate engineers are involved in many aspects, from building dams to hold back water, to turning the water into energy with turbines, making the electricity flow all the way from the north right into your house, right into that switch. So when you flip the switch, you know the light is going to go on. For the most time it does. There's maybe an odd storm and it has an impact to some of the distribution of electricity, but you expect that light to work all the time. When you turn a tap, you expect water to come out. You expect water to come out that's safe to drink. Chemical engineers, civil engineers design pipes, design the chemistry in the treatment plants to make sure that our water is safe. Even walking on the sidewalks, engineers get involved. The school bus you may have ridden, or the car you live in, is designed by engineers. And the schools, if you look up at the ceilings, what holds the ceiling there? Well, there's some architectural details and drywall and paint, but in behind all that is a steel element or wood sections that have been designed by engineers to ensure the roof stays up even when there's wind storms and snowstorms and so forth. So our job is to protect the public. That's what we're here for. Even though you may not see engineers on a regular basis, we kind of work in the background. So providing this opportunity for you to design and build bridges, break them, gives us an opportunity to interface with students, even the teachers and even the parents. I'm sure maybe all have gotten involved in this effort. So hopefully it's meeting our goal by getting you involved.
So what is your favorite thing so far for involving in Spaghetti Bridge?
Well, it's been many years that I've been involved in this. We started back in 1995. So many of you may not even been born then, but we've been doing it year after year, and we're getting more and more students involved. This year, there's over 800 students that have been involved in this. And the number behind me, the 763 kilograms, that amounts to all the loads that every bridge has held, and we've added that up. And we're going to use this on the basis to make a donation to Manitoba Harvest to provide food to the needy. So hopefully we're helping out society in that effort as well. So I think we're waiting for the next class to join us. We're ready to start. All right.
I was just going to say, I'm one of the engineers working behind the camera right now, doing data entry, so you can see that this number continues to go up and up and up. My name is Parker. I'm a professional engineer. I work for a company called AGI. We do grain bins, structures, and other agricultural equipment all throughout the world. So again, different than what Don and C are doing, and that's the great thing about engineering, and Don kind of touched on that there's so many different paths for engineers. You may not think there's something for you, but you'll see if you get into engineering, there's so many different paths you can go down. It's not all just going to be maths or sciences either. You don't have to be, a genius in math or science to be able to be an engineer. There's so many different opportunities for students, for professionals to be able to expand their knowledge and get into different areas of engineering.
Right, there's engineers from all over the world that are installing pumps and wells in third world countries to provide fresh water to local people. So there's many things to be involved in. Sky's the limit. Anything space orientated, anything computer orientated. There's engineering knowledge, experience that people, when they go to university, go into faculty of engineering, get to learn and be involved in. They can choose a career in that area. So, yes, any questions? Please just go online in the chat room, and we can answer any questions you may have. To become a professional engineer, it's typically 5 years of university after high school, and then there's a mentorship program you have to go through and work with other engineers to learn a bit more before you become a professional engineer. Once you're a professional engineer, then you're obliged on behalf of the public to be responsible for what you design. You have to put your name, you have to put your seal on your designs to prove that you're competent to be able to provide the necessity experience to know how you're designing something. All right, okay. So we're ready to continue breaking bridges. All right. Is this a new class just coming online now? Okay, so hi everyone. My name is Don Spangelo. I'm a professional engineer. I'm going to be running this machine here to break your bridges. And if you have any questions, please go on the chat line. As a civil engineer, I'm involved in designing generating stations north of Manitoba Hydro that hold back water that is used to generate electricity and provide power to everyone's home. And I've been involved in the Spaghetti Bridge event for many years. And as an engineer, designed this machine to accommodate all your different types of designs and to make sure that we can test the bridges fairly and to get a readout, a load of exactly what each bridge carries. As we load this frame, you can see the numbers go up, and the number you see at the end after it breaks shows the peak that the bridge achieved just before it failed. Right, and would you like to add something?
Perfect. So I'm C, and I'm a biomedical engineer, and I'm Don's assistant for today. We can start. The first one will be Luke. We can start with General Vanier School, and then this is Luke's bridge.
All right, okay. Hi, Luke. So hopefully you're online, you can see this, and I'm sure you're anticipating to determine how much load your bridge could take. So I know these take a while to build, and yet it's going to take me seconds to break. So, sir, we have to break them, but that's the ultimate goal, and see how much load they can carry. Uh-oh. Now, maybe I'm going to try to reset it a bit. I don't know if it may help or not, but I guess I'm anticipating that there's just a few strands left at the end of the bridge here that are going to have to hold it. Even though the bridge is good and solid in the middle, it's important to continue that structure right over on top of the supports, because the concept is the load that comes down here is transferred to the supports at each end. So it has to have a good, efficient route to get there. And yeah, I don't know. Yeah, no, that's about all we're going to get. So 3.1. Very good. Excellent.
Perfect. So the next bridge is from 3 different students: Ayudale, Juliana, and Cadence.
All right. Okay. So very typical A-frame, which we see many of. And we'll see some more, I guess, coming up shortly. We'll see how this type of bridge structure stands load. All right, and we'll see the end kind of failing there, so 7.5, excellent, very good. Cool how it broke. Take note which pieces broke. Maybe building a bridge next time, you can make it a little bit stronger in that area and work towards having a bridge that can carry more load.
And the next entry is from Porter.
All right, okay, here we go. Now, let's see here, we gotta get the peak of the bridge directly underneath the load. Just have to move it like that. And here we go. Uh-oh. All right, wow, 8.6, very good. Excellent job.
The next bridge, I am sorry to say that it's been disqualified due to it's too tall.
Too tall.
Yeah,
Okay.
this is from David and Jana and Reed.
All right, okay. So now take note. One of the reasons we have certain rules on height is just to make the bridge all consistent, and as I mentioned earlier, to make them keep them all within the same criteria. Obviously, a taller a bridge is, that gives it an advantage to carry more load. So that's why we limit how high it can be, so that everyone is more fair to everyone's design of bridges. And also, there's a limitation in our machine. It's only designed to accommodate bridges a little bit taller than beyond what's specified. So this one still works, so we'll try it. And I have to reset it just a second. And we'll see what it can carry. Here we go. Oh, oh, oh. You know what? I'm going to reset it again. Kind of slipped at the top. Try to fit it in this way. And I don't think we're going to get any more out of it because you can see, again, the bridge at the very end here, there's just a few pieces of spaghetti sitting on the support. Ultimately, these elements here, I would suggest that they should come spreading out so that they sit on top of the structure, on the top of the support structures like this. That would give the bridge a lot more strength. Here, we're just relying on just a few pieces. And my concern is that that's going to break at the end there, and then we end up with the bridge too short. So I don't think we're going to get any more out of that. So I'm very sorry, but there's some ideas for others and yourself to build a bridge a little bit different next time and get the structural elements coming way out over the supports.
Perfect. The next one is from Sophia, Selena, and Lily.
Right. Okay. Here we go. Uh-oh. I see some crunching and then the end breaks there. So 8.0 kilograms. Very good. Nice A-frame design, and I see we have extra pieces added here to enhance it a bit good. So very good design.
And this entry is from Scarlett, Lydia, and Wampy.
All right. Okay. So we're going to see what happens here. Again, that's kind of reiterating, you know, the few elements that come in there on the end. Very important to watch obviously what happens in the middle, but also what happens at each end. Those are two areas of importance. Oh, there we go. 1.1. All right. Very good design. Very unique. So nice to see.
This is from Charlotte, Autumn, and Mia. Unfortunately, it's disqualified because it's too tall.
Yeah, okay. Now, see, we can't really get it into the machine to properly test it. So what I'm going to do, I'm going to use some judgment. I'm going to break off a few pieces right at the top here, which would not necessarily affect the structure because it's not down where the main loads are being distributed. But I'm going to try to just gently break a few pieces here and see if we can get it into our machine. And it's solid glue. So I'm going to see if I can do here. So I'm going to apply a little bit of load that you'll see on the machine. But now as I load it a bit more, we're going to see if keep slipping. Okay, so 12.7 is kind of, I would call the official load because we did break some pieces off of it. But take note, the structure is relatively still in place. So we're going to see if we can get a little more load out of it. And this may or may not help. We'll see. But it'll give you an idea of what the basic structure, the design can hold. And in this case, maybe the construction techniques could have made, again, these diagonal pieces again come down and sit more on top of the supports at each end. And we keep breaking pieces off here. We'll set it one more just for the fun because we're here to break the bridge and it's not really broken that much yet. So bear with me. Let's see what we can do. So being that this is not sitting right in the center of the bridge, it makes it a little more complicated. Okay, here we go. I think that's about it. Now what's happening is the pieces and the ends here broken out. So 19.5 is very good. And again, it's the these elements here not being able to come directly on top of the road here. So great design, good concept. But just in how it's built, if you just tweaked a few little dimensions, it would have made a bit of a difference. But great design though.
Connor, Fran,
Okay.
I'm sorry, Connor, Francis, and Kingsley, they has also been disqualified because it's too tall.
Too tall, but it still kind of fits in here without having to break pieces off. So, okay, we're ready to test it right away. And there we go, 0.8. Well, yeah, there's a bit of aspects of gluing in the joints can make a difference. The design, again, height, following the design criteria and so forth. So, right, yeah, a good design. Maybe now that you're seeing other bridges being broken and how they're built and how yours failed, next year maybe you can build something even better.
Perfect. Here's an entry from Sawyer.
Okay, all right. Good, another very classic A-frame here with some elements and so forth added. And we do see in this case, we have some of these diagonal pieces coming down and bearing directly on top of the load. So I wouldn't expect the ends of these to break, which you may have seen in others, though it's going to be something else happening within the main body that I believe are going to fail. And there, take note, the ends do not break because of these position of the diagonal, but yet the center of the bridge was able to do its function and hold up to 6.5 kilograms. So very good.
This is from Sawyer. Yeah,
Okay.
this entry from Sawyer. And the last entry from General Vanier School is from Aurora.
All right. Okay. Okay. Maybe there's some comments I've talked about already on the details at the end of the bridge. So hopefully these, it almost is there. We'll see where it fails. It'll be interesting to see. Oh, look at that. That's pretty good. Wow. 15.4, excellent. That's a very good bridge. All right. So, any questions anyone has? Please use the chat line. And, okay, we're going to a different class now.
Yes, that's right. We are going to Echo 7 Oaks Middle School.
Okay.
Yes, the first entry that's from Kayla,
Okay.
grade 7.
Grade 7, all right. Great.
And Kayla, Kaya, and Jenna.
All right, okay.
Yeah, all three of them.
Great design, another A-frame, but take note how the elements come down on top of the support. It's the right height. So I'm going to reset it a bit. Just hang on a second. There we go. All right, broken many pieces. That's a good design. Not just one little piece broke, but a whole bunch did it all at the same time. So very efficient design, putting up to 10.4 kilograms. Very good.
So this bridge I have here is from Tony, Sophia, and Mary. It's been disqualified because it's too short.
Okay.
Yeah.
Yeah, so we see that again, it doesn't fit in here. So being that it spans a shorter distance, that makes it a little more more efficient. But we're going to test it anyways. Take note how we've designed the structure to accommodate bridges that sometimes are a little too short. So this will not be an official load that would allow you to potentially win a prize, but we're still going to test it and see how much it can carry to, we can at least determine the overall concept design of the bridge, how well it works. But take note, next time it's going to have to be just a little longer to be competitive, to be a part of the competition. But it's still a great bridge. It looks like it's going to hold a lot of load. Look at that, 12.6. And we crushed it. All right, very good. All right, great design. All right.
Perfect. The next one here I have is from Basti, Cole, and Noah.
Great. And which school is this from?
It's the same school, Ecole Seven Oaks Middle School.
Great. Okay, we're still in the same school. Right, guys? Hopefully you're all online and able to watch. Just like another great bridge, another A-frame, lots of little elements, including a large brace right in the center where the load is coming down. So we'll see what kind of load is it. All right. Excellent. I think that's about it, right? 24.6. All right, very good design. Kind of neat concepts that maybe others can look at and see what kind of load they can build next time to see if we can carry that kind of load. Very good. Just a second, I'm going to do a little adjustment here. We need to make sure that everything is set right here. It's seen too much action and this needs a little tweaking. All right, okay, you're ready.
Here's an entry from Connell,
Okay.
Ryland, and Liam.
Okay, and I'm assuming the bridge is to be broken in this orientation, so here we go. Oh, I hear crunching. 5.6, very good. All right, a different design, very basic, but yet look at the load it carried. Very good.
Perfect. The next one I have Alicia, Abby, and Maddie.
All right.
Yeah.
Wow, this looks like a different kind of concept. Notice how very laminar they've been able to put the spaghetti together with. And again, some diagonals that come down right on top of the support. And we'll see what kind of load it can carry. Oh, look at that. So the centerpiece broke before the main part of the bridge broke. Look at the load, still 35.5, great. But if they would have had another pillar like this right in the center there, that probably would have helped this one piece that did fail, and it would probably carry even more. But at 35.5, that's excellent, very good. I think that was one of the better bridges that we tested today. So good to see. Hope that was fun to watch.
Perfect. And the last entry from this Hawking group, we have Ella, Brooklyn, and Avela.
All right. So again, this is a classic bridge. It has a deck that you can actually drive. So kind of neat to see. And then it has even some guardrails. It's kind of cool. Great design, and we'll see what it can do. Make sure I get it. Supports. Here we go. I think that's it. All right, 8.5. Very good. Excellent. all these bridges take a lot of effort to build. So great to see. And sorry we have to break them within seconds. But maybe that's the fun part. What do you think? Please provide a comment. Having fun? I'm having fun. I'm sorry, I don't mean that in, I like breaking things, but fun to see some of the designs and how they work. It's great.
Perfect. And we're moving on to the next is Mrs. Brown group. The first bridge I have here is from Graham, Josh, and Ethan.
All right, okay. Cool. Thanks, guys, for joining in and watching us break some bridges. This is another unique design. Very curious to see how it's going to perform. I think that's it. So at 8.6, very good, excellent. I see some diagonal shaped pieces and so forth, so great. Yeah, nice to see.
And this bridge is from Cristiano and Ava.
All right, again, another very unique design. This has some pillars here, and very unique in that one end they have a cross building this M section. At the other end, they have something straight. So very unique. There's variability in the design. It's not all symmetrical, so kind of very unique to see. We'll see how it performs. Uh-oh, it's kind of flexible. Look at that. Okay, all right. 1.1 kilogram, very good. Excellent to see. And it's nice to see something different and unique to try out what may work better than some of the other designs.
And here I have a bridge created by a group of 3, Nolan, Riley, and Evan.
All right. Okay. Here we go. Make sure I get it centered. All right. Uh-oh, I see it breaking right here. There we go. All right. So interesting to see how it broke there. If you were to make the spaghetti sections thicker or stronger in that one area there, the whole bridge may have been able to carry some load. So great to see results, and hopefully there's an opportunity to learn for the next time.
I have the bridge from another group of 3, Cassie, Simi, and DL.
All right. So make sure I get it right here. There might be little pieces of spaghetti breaking a little bit at the top, but it'll hold more load once you get it. There we go. 5.7. Excellent. Another basic A-frame with some pillars in the middle. Seems to work pretty good.
Perfect. And the next bridge is made by 2 students, L and J.
Okay. So this is very unique. I don't know if you've seen one like this. I see some interesting elements in the bottom and a pillar right here directly under the load. And I also see these diagonal pieces coming down and basically sitting right on top of the support. So I'm very curious how this will work. Look at that, a broken tension. Very good, excellent, 15.1. Very unique design, and I think it worked very well. Excellent, guys. All right.
And then the last one I have here is from Izzy and Jasmine.
All right, okay. So I see we have some pillars, and I guess what I'm going to do is I'm going to load directly on top of this one here. Reset it a bit. All right, here we go. Any guesses how much it's going to carry? Oh, there we go. Right in the middle. 4.1. Excellent. Very good. Very different and unique. And neat to see how much load it can carry. Thank you, guys.
Perfect. I think that's all the bridges that we have for today. And I hope all of you, all the school, the teachers, and students enjoy the bridge breaking process as much as I did and Don did.
All right, good.
Yeah.
All right. Okay, so just to give you some more understanding of what we've been doing and how everything has been working, I have some facts here. There was 126 bridges actually broken today. It's great for everyone to be online to see them. And there was some 226 students involved from grades pre-K actually to grade 12. This is the final day of the 2023 competition. We broke bridges on Monday at the Golden Place Mall, and yesterday, Wednesday, at Bruce Middle School. And by the end of today, we have tested some 384 bridges total, being built by almost 800 students. So great to see that. And also, there's some teachers that also built some bridges too. This competition has been held annually since 1995, and this is our 29th year, and third time it's been held virtually. The stronger the trust, the more money the Engineering Association donates to Manitoba Harvest. So we've accumulated 7,464 kilograms of all the bridges, all these some 384 bridges have added up to. And we're going to be using this amount to make a donation to Manitoba Harvest to provide food to the needy. And just to give you an idea of some of the maximum bridges that have broken in the last few years. In 2022, it's 172 kilograms by grade 7 student. 2021, 140 kilograms by grade 4 student. In 2020, 176 kilograms by a grade 5 student. 2019, 180 kilograms by grade 12 student. 2018 was 195 kilograms. And in 2017 was 192 kilograms by a grade 10 student. So great to see you all come out. Hopefully you've learned something on how to build bridges and how to maybe experience what it's like to be an engineer going through this effort. And maybe making it easier for the teachers to give students something practical and very interesting to do outside of the basic curriculum that the teachers have to work with. So awesome. Is there any questions you may have in the chat? Okay, seeing none. Yep, seeing none. That's great. Hopefully everyone's enjoyed watching your bridges broke. We're providing some videos about some other engineers and what their experiences are in being an engineer, and all your information, your data, and so forth for you. And I guess we'll also be identifying the winners and getting prizes out to them. So stay tuned and bye for now. Have a good day. Okay, bye.
From all of us here at Harvest Manitoba, I want to thank all of the participants in this year's Spaghetti Bridge Challenge. Harvest Manitoba relies on thousands of people all across this province to provide us with the food, the volunteer labor, and the funds that allow us to feed over 80,000 people each and every month. I congratulate you on what you're doing, raising awareness and money to support the work of Harvest Manitoba. To all of the contestants in this year's Spaghetti Bridge Challenge, good luck and thank you.